Hello students, this is Mr. Ezra. Lately we have been talking about how to solve polynomial functions that have rational and irrational roots. And today we are going to add complex roots to the mix. Remember, complex roots have a real part and an imaginary part. They have somewhere embedded into the solution a square root of -1 that turns into the imaginary number I. Before we begin, remember that we are still going to use the quadratic formula. We've seen it recently. It's something that you should know by now. And I also want to remind you that these types of roots, square, when you have a radical root or an imaginary root, they always come in conjugate pairs, which means you're going to have a positive version and a negative version. You can see that in the quadratic formula. Every time you use it, you get plus or minus. If you have a complex root, that means that the discriminant, which remember is the part underneath the radical, b squared minus 4ac, is going to be negative. So you know you're going to have a negative under the square root. To get rid of that negative, we just take out the letter I and use I instead of the square root of -1. When we talk about conjugate pairs, what I mean is if there is a real part plus an imaginary part, if that is a root, if that is a 0, then the conjugate of that root, which is the real part minus the imaginary part, is also going to be a 0 of the function. They always come in those kind of pairs. Remember that imaginary zeros don't cross the x-axis. You can't see them on the coordinate plane. For example, if I have an x-axis and a y-axis, and I notice that the function goes up, back down, and back up. Well, that is probably a cubic function. And cubic functions have 3 roots, but this only goes through the x-axis one time, so the other 2 roots are going to be imaginary. And that's kind of what we'll see in the graphs that we look at today. It's not going to go through the x-axis as many times as there are, as the degree suggests that it should. Here's our first example. We are going to find all of the zeros. Now, sometimes we start talking about synthetic division and the quadratic function and putting it in your calculator, and students forget that they've already learned how to look for common factors. And if you have a common factor, do that first. It'll make life a little bit easier on you. Here we have x to the 3rd power plus 9x. And what we realize is they both have the common factor of x. So we divide that factor x out of both of them and move it to the front. Now we have x times x squared plus 9. Well, these are small enough in degree that we can set them both equal to 0 using the zero product property, which means we say that x is equal to 0, and we set x squared plus 9 equal to 0. Well, when we get x equals 0, that means that one of the roots, or one of the zeros, is in fact 0 itself. The x squared plus 9 equals 0 has to be solved by first subtracting 9 on both sides. So we get x squared equals -9. After we subtract 9 on both sides, we're going to take the square root on both sides, which gives us positive or negative square root of -9. Underneath this radical, whenever you have a negative, that comes out as the letter I. So the negative comes out as I. It's like saying the square root of -1 times the square root of 9. And the square root of 9 is 3, so both the negative and the 9 come out as 3i. And remember, this is a conjugate pair. We're going to have both of them, both the positive and the negative. So that means that the zeros of this function are 0, 3i, and -3i. One of them is rational. 2 of them are complex. In our second example, let's kind of review with our calculator what exactly we do. How do we find the fact that -1 and 2 are rational roots that we can use? Well, we've been talking about how to use our calculator to look at the graph to see if we can find some good rational roots. And I've already put in the function listed here, x to the 4th minus 5x to the 3rd plus 7x squared plus 3x minus 10 in my calculator in y1. I've already put that in there. Now, a lot of times I'll start by using zoom standard, number 6, just to kind of see what I can see. And what I notice is if I zoomed in on my x-axis a little bit, I could see better. So maybe I'm going to go from like -3 to +4 or something like that. The y-axis looks fine. I might change it a little bit as well, but I'm definitely going to zoom in on my x. Let's try -3 to +4. Really, this is your personal preference. You're just trying to see the graph and see where it crosses the x-axis. And I think I can pretty good see that it crosses at -1 and +2. A quick way to check that is to hit trace. That puts the cursor on your function, and you type in where you think the 0 is. I think it crosses at -1. When I hit enter, I notice that it is on the x-axis. I get the point -1, 0. I can also check over here. I think that it crosses at 2 there. So I'll do the same thing. I'll hit 2, enter, and I get 2, 0. I want to show you another place that you can go to look for rational roots that are integers. There is a table of values above graph. You can hit second table. And in this table, you can arrow up and down as far as you want. And what you want to look for are values of x where y is 0. We see that y is 0 at -1 and y is 0 at +2, which matches on our graph where it crosses the x-axis. So our calculator does a really good, quick job of telling us the rational roots some of the time. And once we find those, we use synthetic division. So we're going to use -1 synthetically. And remember, once you go through your synthetic division of adding, multiplying, adding, multiplying, adding, multiplying, all the way down, you have a remainder of 0. That means that the root is in fact a root. It does work. We build our second synthetic division off of the outcome of the first, not including the remainder. So what this allows us to do is to go from a 4th degree, this would be a 3rd degree, and now we're down to a 2nd degree, which we call a quadratic, which is 1x squared minus 4x plus 5. And what you'll notice is that when it's written this way, you already have your a, b, and c kind of listed out. A is 1, b is -4, and c is 5. We are going to plug in this a, b, and c into our quadratic formula. And we start kind of with the discriminant, which is the b squared minus 4ac. And plugging that into our calculator, we get -4. We can go ahead and multiply 2 times 1 as well to get 2. And we notice our discriminant is negative, which means that we have an imaginary or complex root, right? The negative comes out as an I. And then we can think, well, the square root of 4 is, in fact, 2. So we got 4 over 2 plus or minus 2i over 2, which is what happens if we break the fraction apart. Well, 4 divided by 2 is 2, and 2 divided by 2 is 1, which leaves us with just 2 plus or minus I. So we started with a quartic, a 4th degree polynomial, and we ended up with 4 roots, -1 and 2, and 2 plus I and 2 minus I. Altogether, those are our 4 roots, 2 rational and 2 complex. In our next example, find all of the zeros of the function. I've already got a graph up of this function. And what I want you to notice here is that it goes through the x-axis at -2. So we know we have a rational root of -2. It goes up, down, and then bounces off of the x-axis at +1, which means that +1 is a double root. It is a root that occurs 2 times. So what we're starting with is a 5th degree. By looking at the graph, we have found 3 of the 5 roots. We don't see it crossing the x-axis anymore, so the other 2 roots must be imaginary. We're going to do synthetic division with the 3 roots that we know that are good, which will take us from a 5th degree down to a quadratic. Don't forget, anytime you do synthetic division, that if there is an exponent missing in your countdown, 5, 4, 3, 2, 1, 0, you have to use a 0 placeholder in your synthetic division to make sure that you get the answer correct. The nice thing about this is we know that we've done the synthetic division correctly. It's easy to make a mistake occasionally, but if you don't get a 0 at the end and you know that the graph is telling you that it should work, it means that you might have a mistake in your synthetic division. You can go back in and check that mistake. So we will build our synthetic division off of the first one and try our second root, which is a 1. With the result of this synthetic division, we'll divide our third, which is the second, or the double root 1, the second root 1. And by running through this process, we started with a fifth degree. After synthetically dividing once, we were at a fourth degree. After synthetically dividing again, we were at a third degree. And after synthetically dividing another time, now we're at a quadratic. So this is the same thing as at 1x squared plus 0x plus 4, which we don't have to do the plus 0x equals 0. But once we get it to a quadratic, sometimes we want to use the quadratic formula, sometimes we want to factor. In this case, we're going to have complex roots, which means that often they won't factor. I mean, they're not going to factor if they're complex. But in this one, I'm seeing that the best method might be the square root method, to subtract 4 to the other side, and then to take the square root of both sides. Now, when I take the square root of both sides, I'm going to get a positive and negative square root. Let's just kind of add that up here in this step. A positive and negative square root of negative 4. Well, we know that with the negative, we're going to get an I. What is the square root of 4? Oops. Square root of 4 is 2. We get positive negative 2i. When we're listing out all of our zeros, or we're listing out all of our roots, remember those words mean the same thing. If I say what are the zeros or what are the roots, I'm asking for the same thing. Well, it's going to be the 3 that we found with our calculator, and then the 2 that we found by working with synthetic division and the resulting quadratic, which is positive 2i and negative 2i. And you should notice that once you finish the problem, that if you started with a fifth degree, there are 1, 2, 3, 4, 5 roots. Even if one of them is a double root, it counts twice. Another example for us today, we're asked to find all of the solutions of 7x to the third minus 18x squared plus 20x minus 24. Well, the first thing that I did, which I'm not going to show you, is I went to my graphing calculator and I found that 2 was a rational root, that it goes through the x-axis at 2. Since I'm starting with a cubic, I knew that synthetically dividing by 2 would give me a quadratic. It would give me 7x squared minus 4x plus 12 after doing synthetic division. So the cubic, synthetically divide by 2, get a remainder of 0, and this is my resulting quadratic. I set it equal to 0 and solve. In this case, non-factorable, have to use the quadratic formula, or probably need to use the quadratic formula. I plug in everything into the negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember when your b is negative, for example, that it's important that you put parentheses around it when you're plugging it in. Your calculator can give you incorrect answers sometimes if you don't use those parentheses. The discriminant ends up being negative 320, and negative 4 simplifies to 4, and 2 times 7 is 14. Now we break this apart, and as I broke it apart into 4 over 14, I went ahead and popped out that square root of a negative as I, root 320 over 14. When I'm trying to simplify 320, I notice that 4 goes into it, but 4 is not the largest perfect square, and 16 also goes into it, but it's not the largest perfect square either. In fact, the largest perfect square that goes into 320 is 64. It is 64 times 5. So I'm going to take the square root of 64, which is 8. And now I have 8 root 5. And I'm kind of showing you this here because this is how I simplify 4 over 14 to give me 2 over 7, because 2 goes into 4 2 times, 2 goes into 14 7 times. I also can reduce the 8 and the 14 by dividing both of them by 2 to get 4 over 7. We still have I root 5. We want to list out all of our roots. Positive 2, 2/7 plus 4i root 5 over 7, and 2 over 7 minus 4i root 5 over 7. Remember that it is okay for you to put 2 plus or minus 4i root 5 over 7. That does represent both of the roots, and it is acceptable, but we've already separated them apart, so we're going to leave it that way. Well, that is it for today. That is how to add in the complex roots. Really, the only difference is when you're simplifying your quadratic formula or the square root method, you have to deal with a negative under the square root sign. I hope that this made sense and that you're able to be real successful with it. I'll see you in class.